When an atomic nucleus becomes too large or accumulates too much energy, it reaches a point of physical instability. To correct this, the nucleus abruptly fires out its excess mass or energy to stabilize itself. It accomplishes this correction through three specific pathways: shedding physical mass, converting a neutron into a proton, or releasing pure electromagnetic energy. Physicists classify these resulting emissions as alpha, beta, and gamma radiation. The word radiation is often used as a single catch-all term. However, alpha, beta, and gamma are distinct mechanical entities, each possessing entirely unique physical properties and behaviors. To understand how these emissions interact with the physical world, we have to look past the generic label of danger and evaluate the strict physical mechanics of the particles and waves themselves. This graph plots penetration range on the vertical axis against the combined mass and charge of an emission on the horizontal axis. Every type of radiation operates within this space, governed entirely by its mass, charge, and velocity. As radiation travels, it undergoes a process called ionization. This occurs when an emitted particle physically collides with an atom in its path and forcibly kicks an electron out of its orbit. The mechanics here are highly deterministic. A larger, more positively charged particle exerts a stronger electrostatic pull, meaning it violently and rapidly rips electrons from atoms as it moves. But that aggressive ionization comes at a strict physical cost. By interacting so frequently, the particle exhausts its kinetic energy almost instantly and grinds to a halt. High ionization directly guarantees a critically short penetration range. This inverse relationship forms the predictive model that defines both the biological hazard and the engineering utility of all nuclear decay. This three-part diagram isolates the alpha emission's physical profile. An alpha particle is basically a helium nucleus, constructed from 2 protons and 2 neutrons. This gives it a massive physical profile, a mass of 4 and a positive charge of +2. When the unstable atom ruptures, it launches this heavy particle outward at roughly 5% the speed of light. Because of its heavy mass, the alpha particle acts like an atomic bulldozer. It plows into surrounding matter, aggressively stripping electrons from nearby atoms. The sheer rate of interaction is extreme. A single alpha particle rips away enough electrons to create between 30,000 and 50,000 distinct ions for every single centimeter it travels through the air. Creating tens of thousands of ions drains the particle's momentum rapidly. Its kinetic energy drops straight to zero. Because it burns through its energy so quickly, an alpha particle has a maximum range of just 1 to 5 centimeters in the air and lacks the momentum to penetrate even the microscopic outer layer of human skin. Now look at the beta emission. When a nucleus contains too many neutrons, it corrects the imbalance by converting one neutron into a proton, firing out a fast-moving electron in the process. This beta particle stands in sharp contrast to alpha. It carries a negative charge of exactly 1, and its physical mass is functionally 0. Lighter and more agile, the beta particle is ejected at speeds reaching approximately 60% the speed of light. Its tiny physical footprint and single negative charge mean it slips past the vast majority of atomic structures in its path without interacting. Unlike alpha's tens of thousands of ions, the beta particle creates a highly sparse trail, generating 50 to 100 ions per centimeter of air. Because the beta particle avoids those collisions, it retains its kinetic energy much longer, extending its physical reach. This balanced ionization rate allows a beta particle to travel further, a full meter through the air, 2 centimeters into living tissue, and 3 millimeters of solid aluminum to successfully absorb and stop it. Finally, there is gamma. Unlike alpha and beta, gamma is not a physical particle at all. It is the highest energy electromagnetic wave. A nucleus releases a gamma ray strictly to vent pure excess energy. Consequently, the gamma emission possesses exactly 0 mass and exactly 0 charge. Without mass or charge to cause electrostatic friction, the gamma wave easily phases right through the vast empty spaces that exist within atomic structures. Interactions are exceptionally rare. A gamma wave produces a microscopic 3 to 5 ions per centimeter of air. This frictionless trajectory allows the wave to maintain nearly all of its initial kinetic energy over massive distances. Gamma radiation travels hundreds of kilometers through the open air and cleanly passes through tens of centimeters of dense living tissue. Stopping a massless, chargeless emission requires extremely dense matter. 1.2 centimeters of solid lead cuts the intensity of a gamma ray exactly in half. We can map these physical limits to human biology using this split-screen anatomical model. The left side tracks irradiation, where the radioactive source remains outside the body. The right side tracks contamination, where the source is internalized. Alpha radiation presents an interesting paradox. It is the most intensely ionizing and locally destructive emission, yet an alpha source sitting across a room poses absolutely zero external threat. The physical model explains why. Alpha's immediate energy loss prevents it from crossing the air gap, and even if it reaches a human, it bounces harmlessly off the microscopic outer layer of dead skin. But if an alpha source is inhaled or ingested, the mechanics reverse completely. Trapped directly against living soft tissue, its 50,000 ion per centimeter rate causes severe, highly concentrated cellular destruction. Gamma operates in exact contrast. As an external irradiation source, gamma is highly dangerous. Its frictionless nature allows it to sweep straight through the external skin barrier and strike deep internal organs. Yet as an internal contamination source, gamma presents the lowest risk. Most of the waves emitted inside the body simply pass outward through the tissue and exit into the surrounding air without ever striking a cell. The beta particle occupies the middle ground. Its moderate mass and charge result in a balanced penetration profile, meaning it poses a moderate hazard in both internal and external scenarios. Biological radiation danger is strictly contextual. The severity of the threat is dictated entirely by where the mass and charge interactions take place relative to human cellular structure. Engineers rely on these exact deterministic limits to build reliable tools, actively exploiting the physical constraints of alpha, beta, and gamma emissions. This blueprint details a standard home smoke detector chamber. Inside, an active alpha source emits a continuous, short-range beam toward a nearby sensor. Alpha is selected specifically for its limitations. Its strict 5-centimeter range makes it inherently safe for residential use. Because its penetration is so weak, even the wispiest smoke particles drifting into the chamber physically block the heavy alpha particles, triggering the alarm. In industrial manufacturing, we use this setup to measure material thickness. A beta source sits above a moving sheet of paper with a detection sensor directly below it. A perfectly calibrated sheet of paper will absorb exactly 50% of the moving beta particles. If the paper thickens slightly during production, the denser material absorbs more particles, immediately altering the sensor readout and flagging a manufacturing error without anything ever physically touching the paper. In medicine, physicians harness gamma radiation by safely injecting a radioactive tracer directly into a patient's bloodstream. Gamma is uniquely suited for medical imaging. Its massive penetration range allows the rays to travel entirely out of the patient's body and strike external sensors, forming a precise 3D map of the internal organs. Nuclear radiation is a highly deterministic spectrum of physical interactions. By mapping the exact limits of mass, charge, and energy, humanity has reverse-engineered atomic decay into precise, controllable technological power.